Welcome back, chemistry fans. Sorry about the surprise there. Today, what we are going to do is we're going to build expanded octet molecules, models. So let's get jumping into it. I'm going to share my screen over here onto the surface where you can do the hands-on display with yourself together with me. So you're going to grab this bag and it's full of all these little beads and connectors. So we're going to try and utilize those right now. So we're going to build two different models that are going to be representative of the two different expanded octets that we have. So we're going to take one of the black center beads. Now yours may not be black, but it's going to have 4 on each side. So you'll be able to do this with it and see that there's a hole on top and a hole on bottom. It's going to have 4 all the way around it. And so that's how we'll know that we've got one of these that we're going to start with here. And what we're going to do is we're going to put connectors onto it. These are going to represent the bonds that are on these molecules. And so it's going to have 4 bonds going all the way around. Whoops, I'm going to switch one. So if you run out of the same color like I just did, we're going to use the other color so that I don't run out and so that they're all the same color. So it makes it a little bit easier for you to visualize what's going on. So I've got 4 going around it, and then it's going to have 1 bond coming out of the North Pole, 1 coming out of the South Pole. Now what we're going to do next is we're going to connect to it each one of these different beads. And again, you're going to want to find one that has at least 6 of these little beads, and these would represent the atoms that are bonded to it. Okay, so now what we've just created is something called an octahedral molecule. And in an octahedral molecule, it's weird because it only has 6 atoms. So why do they call it octahedral? Well, because it has 4 going up and it has, then flip it over, 4 going down. And so that's in their weird world. That's what they've created here. So again, you created a top, if you will, which you could take and you could try and spin it very nicely, just like we did with the, there you go, with the other molecules that we had, the tetrahedral. This one works very nicely as well. So what I need you to do next, though, is for us to visualize what happens whenever we lose these bonded atoms and they are replaced with just pairs of electrons. Now, what you're going to have to visualize is on this molecule, we're going to lose the atoms on the north and south pole. And so what we would have, that was octahedral, but if we then replace one of those atoms with just a tab here, and this is representing the unshared pairs of electrons, what you would see in this example is that we now have a square pyramid. If you can visualize that these are connections, you could see that maybe this makes something of a square-shaped pyramid. Well, if I lose another atom to this process, what we end up with then is a molecule that would be called just a square planar, square planar. And you could see that no matter how I represent this, it looks like an X, or you could connect the dots around it, and you would see that it makes an X. Well, if I lose one more of these to an unshared pair of electrons, and unfortunately, we just don't have a whole lot of these unshared pairs of electrons for us to do, but I will replace it and show you what will it be. We would take this one out, and what you would end up with then is something called a T-shape. T-shape. Interesting. Now, what if I were to lose one more, but still have all of these extra electrons somehow floating around it? Well, then this shape goes back to something that we have called before. This is a bent shape. So it has all these extra electrons floating around, and it becomes a bent. And if you have lost another one, well, then you're just linear. So that one's an easy one to find, but those would be very rare. More than likely, what you're going to find is either the octahedral shape being given to you, or you're going to find this T-shape, or the most likely scenario that you're going to find is the one that we already talked about, which is the square planar, or we might find ourselves dealing with the square pyramid. Those all come about on the octahedral. Okay, so that's your octahedral. All right, now let's create then the other option out there, which is the trigonal bipyramid. So I'm going to put that one off to the side, and we're going to go with the trigonal bipyramid. In the trigonal bipyramid, you'll notice that it does not have the capability for me to hold these four on all sides. They're at an angle, so it has a top, but it's not going to have an empty space on bottom if I put all four fingers around. But we're going to fill it up with all these different bonds. So go ahead and put it around here. And what you'll notice is it doesn't have 6 bonds around it this time. It's only going to have 5 bonds around it. And so you're going to end up having this shape here. We need to fill it up with the other little spheres, and they hopefully are different colors. I hopefully created enough in your bags to do this. So we'll put these around, put this around, put this around, and we'll put this around. So now we have what is called a trigonal bipyramid. And you're saying, well, that looks just like the other one. It doesn't. The other one has more. So if we were to set this up on edge, you would notice that this octahedral coming straight at the camera has one out the bottom and one out the top. If I look at this octahedral, if I put one up the camera and one down at the bottom, it has a triangle. So you notice how this one had the X, it has the square. This one only has a triangle. So it has one less bond on it, and that's why this is the octahedral. This is the trigonal bipyramidal. Now the same scenario develops though. What if I lose one of these atoms and it is replaced with a lone pair of electrons? So it went from an octahedral from a trigonal bipyramidal to now something that's not the same shape. So what they do is they turn this into what they say is a teeter-totter. It looks like a seesaw. So notice how this one has the two coming straight out the north and south, and then it has a left and a right at an angle. And they say that this one looks like a seesaw. So that is the actual name of this shape. It's called a seesaw. Now, if I were to lose one more, it doesn't lose it out of the equatorial plane. It loses it out of the triangle. If I lose one more, what I'm going to end up having is that same T-shape that we discussed in the octahedral. So this is a different version of the T-shape, but it's still just a T-shape. Now, if I were to lose one more, again, it doesn't happen out of the equatorial plane, the north-south plane. It comes out of the triangle. And if you'll notice now, what we have left over is linear. It's a 3-atom line. So it's interesting how the old names come back into these expanded octets. So I'm going to replace these, get these back out to where they originally were. I'm going to place my unshared bonded electrons into the baggie so that we don't get them mixed up, so I don't lose them. And what you're going to have now is the representation of the octahedral. It loses electrons on the north-south, and then we're going to have the trigonal bipyramidal, and it loses electrons on the triangle on its waist, on the horizontal equatorial line. Okay, so that's what you need to be able to understand and visualize moving forward. This is everything that I wish to share with you today for this little activity. Thank you very much for your time. I will talk with you again soon. Bye-bye.